Hello everyone to a new video. Today I'm going to be looking at further maths limits. So this is going to be limits, all the techniques you need to know to evaluate a limit, all the basics that you need to know. So first we're going to start off with seeing what are limits. So before this, you probably have seen limits in AS, but let's just start off by refreshing our memory. Limits are used to see where a graph or where a function would go if x tends to a certain value. So if x tends to a value, or if x tends to infinity, or minus infinity. So these are the most common ones, most common limits that we look at. So for example, if we have a function here of e to the power of x, and we want to see what happens as x tends to infinity. So what happens as this function goes to positive infinities, so goes to a very large number, y, the function, tends to 0, but it never equals 0. That's why we say tends. So that is just basically what a limit allows us to do. And when I say positive infinity and negative infinity, we're basically looking at if we had to go to the left-hand side, then we mean negative infinity because we're going to a very small number. But if we wanted to go to the right-hand side, then we mean positive infinity because we're going to a very big number. Same thing for y. This would be positive infinity for y and negative infinity for y. And sometimes there are functions that have asymptotes. So if we have a function approaching this asymptote, it can either approach it from below the asymptote, or it could approach it from above the asymptote. So if this was, for example, 1, if the asymptote was y equals 1, then if we want to say approaching the function approaches the asymptote from below, then we would say y tends 1 from below, or if we want to say it approaches from on top, y tends to 1 from above. So we write these minus and plus signs to be more clear from where we're looking at. And the same thing applies for if we want to see a function approaching 0 from the left-hand side, then we say x is approaching 0 from the left. But if it's approaching 0 from the right-hand side, we say x is approaching 0 from the right. So positive for the right, negative for the left. So I hope that is clear on the different symbols that we use for limits. Now let's look at some common limits that we should keep in mind. Now if you take a look at this, where x approaches 0 from the right hand side for x, ln x, if you take a look at the function, as I'm drawing it out here in a graphic calculator, as x approaches 0 from the right hand side, the function approaches 0, so this limit tends to 0. So now if we were to look at this function, where I have just named x as 2, x approaches infinity, y tends to 0. So again, this limit tends to 0. And this k is anything over 0, so if you put 3, 4, 5, all of it will work. Now let's look at this function. If you have x goes to infinity, where q is an integer greater than 0, then this whole function should tend to 0. Now if you were to look at this, where e to the x minus 1 over x, as I've drawn here, as x approaches 0, the function goes to 1. So we have this limit equals to 1. Now, so these are some limits. That was just a basic introduction of what limits basically tell us. But if we were to if we were given limits in an exam, how would we go to approach this if we weren't able to graph? So that is what we're going to look at in this video. Now, there are a few rules to remember when evaluating limits. If you have a limit that tends to the form of 0 over 0 or infinity over infinity, we use something called the L'Hopital rule. Now, this is a undefined form because we don't know what 0 is bigger than the other 0. We don't know whether this 0 approaches faster than this 0. So this is an undefined form. So when we have this, the rule of L'Hopital is very helpful. And in the rule, we basically differentiate the top and the bottom of the fraction. So let's look at an example. If we have a limit where x approaches infinity, then if we substitute infinity into our x's, we get infinity over infinity. So something you have to do before you use the L'Hopital is test whether you are getting these undefined forms, because then only can you use this rule. So we do get infinity over infinity. So that means we can use the rule. So the rule is differentiating the top and the bottom of the fraction. So differentiating this gives you minus x squared plus 2, and differentiating this gives you 4. Now, if we were to look at x again, as x approaches infinity, this entire numerator approaches infinity. So this entire fraction should approach infinity. So this limit just equals infinity. So that is the L'Hopital and how you use that rule. Of course, this can be any fraction you have. All you have to do is differentiate the top and the bottom. And something you should remember is sometimes you have to use the L'Hopital twice. So if you were to get infinity over infinity again, then you can differentiate the numerator and the denominator again, and then test again to see if you get a defined limit as the answer. Now let's look at the second case. If you know the theory behind the Maclaurin series, it's only used when you are looking at a function that is when you're looking at the range close to 0, close to the origin of the function. So if we have this function of 1 over x, if you want to approximate 1 over x, then, and using Maclaurin series, then you're approximating the function near the origin. That is the Maclaurin series. If you were to use the Taylor series, which isn't in your syllabus, but the Taylor series is basically a more accurate way of approximating functions, but it approximates functions in a more wider range, but Maclaurin is only really useful to approximate functions near the origin. So when we have x tends to 0, we're looking at the function near the origin. So that's when we can approximate the function using Maclaurin series. So an example for this is a limit as x approaches 0. So if we have x, ln x plus 1 plus x over x squared. Now, using our Maclaurin series, this is just given in your data booklet for AQA, the Maclaurin series is given. So again, this is just a simple approximation using Maclaurin series. And once we've simplified that and we have cancelled the x's, we get this. Now we can substitute x as 0 as we're approaching 0. And the only thing we have left is a half. So the limit equals a half. So that is another way that you can use Maclaurin, that you can evaluate limits. Another way is to factorize and cancel out the x's. Now, if you were to have x approaching 0 as your limit, we divide the lowest power of the x. Now, what I mean by this is, you can look at this example. If we had x cubed plus x squared plus x all over 3x squared plus 4x, and we want to find the limit as x approaches 0, we can divide all these x's by the lowest power of x we have, which is just x to the power 1. So we divide all terms by x to the power 1, and we get this. And then we can see as x approaches 0, these terms all equals 0. So the only thing we have is 1 over 4. So the limit equals 1 over 4. But if we had x approaching infinity, then we divide by the highest power. And this is because, again, if we look at the same function, and the highest power we have is x cubed, so we have 1 plus 1 over x, dividing by x cubed, and again dividing each term by x cubed. This is what we have left. Now as x approaches infinity, then 1 over x would approach 0. So when you have x approaching infinity and we have the function 1 over x, this approaches 0 because 1 over a very, very large number gives you a very, very small number. So this approximately approaches 0. So here we have 1 plus 0 plus 0 all over 0 plus 0. Now 1 over 0 is undefined. But again, we need to remember that this is not really 0. This is tending to 0 because we have x tending to infinity. So when we have something tending to 0, we are looking at a very, very small number. So 1 compared to a very, very, very small number is quite big. So a very large number divided by a very small number gives you a very large number. So we say this limit tends to infinity. So now I hope you can see the reason why we divide this by the highest power is because we want to get the form of 1 over x to the power of something. Because when we get this form, x tending towards infinity would give you a small number, so you can basically cancel these out to be 0. And in this case, when we have x tending to 0, we divide by the lowest power because we want the whole x's by themselves, so we can cancel them out as they all tend to 0. Now the fourth rule that you should know to evaluate limits is if you have the same degree of x, you take the coefficients. So now this applies to when you have x tending to infinity, because when you have x tending to infinity, 1 and 0 are basically negligible when compared to infinity. They are such small numbers when compared to infinity. So all we have is to compare these two. So when we have x squared and x squared, so if we are neglecting 1 and 2 here, we only have this left. And now what we can do is just cancel out the x squares, and we're left with 3 over 4. So that is another way you can evaluate limits. Now I want to look at some improper limits. So there are 3 cases of improper limits that you should know. If you have an undefined, if you have infinity in the lower limit, or in the upper limit or the lower limit, then you have an improper limit. So the way we can solve this is assigning infinity to be a constant, for example b, and then finding the limit of that integral where b tends to infinity. So you're basically finding a very, very close approximation to the integral by tending it to infinity rather than solving for infinity, which is an undefined form. So let's look at an example here. So we have the upper limit as infinity, so all we have done is replace that by b, and we have said let's find the limit of this integral where b approaches infinity. And now what you can do is simply solve this integral by parts. So all we're doing is solving this as a normal integral, and I have just done simple by parts here. If you are unfamiliar with such integrating techniques, look at my Further Calculus All You Need to Know video, and that summarizes basically everything that you need to know for calculus, for maths, and further maths, so do check that out. So all I have done is integrated this, and we have our simple by parts method, and we just have the limits of b, of the upper limit as b and the lower limit as 0. So again, simple integration rules, and this is what we are left with. Now what we can do is use this and say we want to find limit as b approaches infinity. And as b approaches infinity, this tends to 0, this tends to 0, and we have 1 left as a constant. So this entire limit approaches 1. Now another improper integral is if you have k, but where k is undefined. So we have a limit where the upper limit is undefined. So we have a function where the upper limit is undefined. So now let's look at a function that does this, which is 1 over x. So this is the function of 1 over x. Now 1 over x never really approaches 0. It gets very, very close to 0, but it never really crosses 0. So there is a very, very, very small part where the function and the y-axis never really meet. So when we're finding the integral of 1 over x with the limit of 1 and 0, we are finding the area between this 1 and the y-axis. So this, we can never really know the exact area of this when solving the integral because it never really crosses 0, so we don't have an exact area to take out. So we have to use this. So we have to use limits to solve this and give us a very close approximation to what the area would be. So let's see how we can solve this. So if we have 1 over x, then all I have done is replaced the constant, which is undefined in this case, which is 0, because the function never really approaches 0, so 0 is undefined for this function. That is very ugly handwriting, but I hope you can see I meant undefined here. So we just replace the undefined constant with b, and we say b approaches 0. So now all I've done is integrate this to be ln x, and as b approaches 0, we get ln b minus ln 1 for this, and as we know, ln 1 equals 0, so we have ln of a very, very small number, and ln of a very, very small number is a very, very negative large number, so it's minus infinity. So really that makes sense because the area is infinite because the function continually moves up. There is no end to the area, so the area would be infinitely large. And now the last example we have to look at, we have a function that is integrated with the limits of a and c, and there is k, which is between a and c, which is undefined. So what we do with this is that we split it into two limits where that k is evaluated for both limits. So we just make b, we assign k as b, and we make b approach k, plus we assign the lower limit now as b, and we make b approach k. So we are sort of, if we have a function that goes something like this, and we have an asymptote here, and this is k, and this is a and c, what we can do is find this area plus finding this area. And since these never really cross k, we would find the limit of both of these and add them together to find the approximate of the area. So let's look at an example here. If we have this function, if you graph this, you can see that this function is undefined at 3 because it has an asymptote at 3. So what we can do is split the function at the point of 3 from 0 to 3 plus from 3 to 5 to find the whole area of 0 to 5. So we have these two different limits to evaluate. So now, as you saw in the rule, what we have to do is assign the undefined constant as b and make a limit where b approaches 0. 0. So now all I've done is integrated this normally, and we have ln x, which is 1 over x, plus 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 1 over x with the reverse chain rule. Again, if you're unfamiliar with that in the calculus, please look at my calculus video and make sure your calculus is strong before you go on to limits, because there will be many complicated functions that you will have to integrate and differentiate. So again, all I've done here is use the reverse chain rule, where you add 1 to this and you divide it by the whole function, and this becomes 2/3. And now all I've done is sub in b and 0, and we just evaluate the limit of where b approaches 3. So 3 here would give you 0, so this gives you 0, and here would give you 9 to the power of 1/3. So all we have left is minus 3/2, 9 to the power of 1/3. So that is this part evaluated. Now look at this part. Again, same thing, we make b approach 3, and then we evaluate the integral like normal. So here in this case, as b approaches 3, this becomes 0, this term becomes 0, so all we have left is 3/2, and 5 minus 3 is 2, so 2 to the power of 2/3 is the same as 2 to the power of 1/3. So we have 3/2 times 4 to the power of 1/3. Now we have this and this. All we have to do is add them up to find our final integral. So all I have done here is add the two answers up, and this is our final answer for the limit. So obviously this is a bit more lengthy, but again, it is very simple, basically the same concept of you replacing whatever x is undefined in the function with a limit. So that is all for improper limits, and all for the limits that you need to know in general to evaluate any limit in Further Maths A2. I hope everything was clear in this video, and I hope this video helped you. If you have any questions, if you want to clarify anything, please leave a comment down below, and please check out the description for any of the videos that I mentioned in this video that might help you in your A2 Further Maths journey. And yeah, again, if you have any questions, leave a comment down below, or you can email me, which I've also put in the description. Thank you very much for watching this video. Bye bye.